Okay, almost everybody's here, so this is sort of unnecessary. But on the off chance that you want to go back and at least listen to the boring part of the lecture, here it is recorded for you. So today we're going to talk about water demands. Water demands are important to us as designers because they help us size how big we're going to make something. The demands to some extent are dictated by the intended use. If we were to categorize or classify the uses in some major categories, we would have withdrawal, non-withdrawal, consumptive. Withdrawal is the water that we take away from a source, stream, lake, aquifer, or our main supply point and move it to satisfy our users. And we assume that withdrawn water isn't necessarily returned to that location when it's been used. So for example, using Lubbock, we all established that we're getting water from Lake Allen Henry right now. It comes up the hill, it goes into our homes, we run it through our kidneys and colons, not necessarily the same water, that would be just sick. And then we discharge it into our wastewater system, and that goes into Yellow Horse Draw. It doesn't make it back to Lake Allen Henry in our lifetime. Or maybe it does evaporate and rains down there. So that use is a withdrawal as far as Lake Allen Henry is concerned. That water doesn't get back to it in any reasonable amount of time. Non-withdrawal, on the other hand, is the water gets back to the source relatively quickly. Examples are navigation uses and recreation. So when you go down to Lake Allen Henry and you drive your bass boat around and you tow somebody behind it who's duct taped to a piece of plywood, because water skis are expensive, but you can find plywood on the side of the highway. That's a bad idea, by the way. But anyway, you're dragging around the lake, you're using that lake for recreation. So there's no consumption of the water. It didn't leave the lake. You might get splashed up in the air and on your swimsuit, but eventually it gets back to the lake fairly rapidly. So that is what's meant by a non-withdrawal use. And then the next category is consumptive use. That's kind of a funny classification. So that's the portion of the withdrawal that doesn't get available for further use, at least in the near future. So if we take water out of Lake Allen Henry and we put it into my tomato plants in the backyard and we make a tomato with it, that tomato contains water that came from Lake Allen Henry. That would be considered consumptive water. Not only that, because I'm going to consume the tomato, run it through kidneys and colon, and then put it back into Yellow House Draw. So that's consumptive use. So the water that gets incorporated, I'll get to you in a second, it gets incorporated into crops and animals, the actual biomass, that's considered consumptive. Water that's used in heat exchange. So you make electricity. It turns out that if you don't cool the turbines, they have this bad habit of melting into a puddle of goop. So you're using a portion of water to cool it, and that water gets evaporated off, and that's what makes those big old steamy things at the power plants. That's really not pollution that they're spitting out in the air, that's just water vapor. Now, smart power plant operators can go, hey, put a little bit of pollution in that because nobody's going to notice. And that's how they get rid of their waste. Yes, ma'am.
What about rainwater? Water that's used by the city that can use.
What would that be? That's a good question. I would say that that's probably in the withdrawal category, because it's just going down its use chain before it gets back to the environment. Just up to all you environmental people to make it at least acceptable to reuse by the environment, or ship it down to Brazil where they have different laws and nobody cares. No one's here from Brazil, right? I just dissed Brazil. That was not my intent. So to look at some of those ideas, in case of a city as an example, if we were to consider a generic urban area, and this diagram is right out of Gupta's book. I imagine the edition you have, they've probably redrawn it, but it's pretty much the same diagram. The circles here, those are mine. You have a municipal requirement for a city. That's the water that goes into our homes, the water that goes into commercial operations. Yeah, you can barely read it, so that's good enough. Commercial operations, and here in this example, the author has proportioned each of these as a fraction of whatever total's coming to it. Commercial in the municipal use sense, restaurants, hotels, car washes. What else do you have? Walmarts and so forth. So it's not the same commercial that you might think in terms of small industries, which is the next category. So the next category, I guess that would be car wash, automotive repair, cottage industries, which is a fancy name for a big industry that's in the little teeny place that makes widgets. So all those things that are sold on Etsy, that would come in the small industry category, except for the ones that are imported from China and then resold as American handcrafts. You can usually tell those because there's a little sticker on top of the made in China that says made in USA and has a flag on it. And the sticker itself is made in China. I mean, it's just hilarious. And lastly, public use and losses. And this particular category is showing 17% for that category. If you get in the water supply business years from now, losses greater than 10% concerns you as an operator. It actually scares you. You hire consultants to go ahead and figure out where that water went, or at least where the billing went. 4% would be considered a good community. So something the size of Lubbock that only had 4% annual water loss, we'd be going, that's awesome. We don't have any leaks that matter. I know in my neighborhood alone, there's a place that leaks pretty much every week. And you would think at some point the public works people will go, well, we keep going and doing a spot repair on this one hydrant. Maybe we should just close the street off and dig everything up and screw up traffic for 2 weeks and just fix it. Although that'll just move the leak somewhere else. That's pretty typical in an urban area. So this is a good job security business for a civil engineer if you get into it and you work in a decent sized city. You'll never get all the stuff fixed. You'll always have a job as long as engineering is required. That would be a good thing. So these circles on the diagram. So this particular diagram is taking water from a river, which sadly runs underneath the city. They should have put it right in the middle because then we could call it a river runs through it. They're taking 35 cubic feet per second. A portion's coming from the river and another portion's coming from this well field. And it's going into the municipal use. And that 35 cubic feet per second, they get 30 of it, comes back out and gets back to the river. And this diagram is also showing a portion of 70 cubic feet per second going to large industries, industrial waste treatment. The flow diagram is wrong. After it goes through industrial waste, it usually goes through a municipal thing and then goes on out to it. And then this particular community is using up 150 cubic feet per second. The cubic feet per second isn't terribly important. It's the ratios. It's using almost 5 times as much water for making electricity to watch all the YouTube videos that these households do. So while they're watching YouTube videos on the pot, they use 40% of the drinking water. That is probably a reasonably appropriate breakdown for the different use categories in an urban area. A lot of water is used for cooling. A fairly large amount of water is used for industry, and what's left gets used for just living. The thermal water is usually returned right back to the source, relatively close to the source. And so when it's returned, it might have gained 10 or 12 degrees of temperature by the time it's done its cooling thing. And normally it gets just put back into the source, and that has good and bad effects. If you like fishing for flounders and stuff, that thermal addition to whatever the receiving stream is usually pretty handy, because fish don't like to get cold either. You go, well, there's yummy water over here that I can actually breathe because it has enough dissolved oxygen in it. Or there's this warm water over here. I know what I'll do. I'll swim to the yummy water, take a breath, or whatever the fish equivalent of that is, and then go back to the warm water, hang out, make more fish. On the other hand, it also reduces the biodiversity of the receiving stream, because now you have fish going back and forth and they got to eat something. So they eat fish food. Industrial water also usually goes back relatively close to the source. Municipal water, not so much. So how do we figure out how much water we need? Well, we use arithmetic. The simplest equation in the history of simple equations, and the only one easier is 1 = 1, relates the number of users to the volume required. So if you take the volume required per person, so that's the V over P part, and then you multiply by the number of persons, which is P, you get the volume back. And so we need to be able to estimate what the volume per person is and how many people there are, which are two different questions that need to be answered. Random dude, okay. Which are two different questions. The population estimation is a population modeling question. It is not something civil engineers are expected to be competent at, which is unfortunate, because unlike population projection engineers, we can at least do arithmetic. So we'll get onto a little background of that. And then the use per person is a different thing. In your lifetimes, so I had a revelation in the class yesterday afternoon. I was making reference to something in the 1990s, and I thought they were all in grade school in the 1990s. And finally the class said, we weren't even born then. It's like, okay. So I'm going to put you all in the 2000s. Is that close for most of you? So you all have grown up in a time when water conservation was a big deal. It's not because people of my generation or my parents' generation actually cared about conserving water. They cared about conserving money. And the water supply, it became evident that there wasn't going to be enough, that we couldn't be using 500 and 600 gallons per person per day. So they went all these water conservation programs. You got little fish that got names. We named them in grade school. You know, Eddie, the edamame fish. I've just mixed a couple cultures right there. And we had a little heron, which we got to name that too. And that was all part of the conservation program. And ultimately, we reduced water use, at least in the United States, to less than 200 gallons per day per person, which is actually a pretty significant reduction from the 1970s. So that's pretty cool. It's probably likely there'll be a little bit more reduction, but as a society, we're probably pretty close to as little water use as we can get without fixing all the leaks in our homes and without making it culturally acceptable that it's better to have rocks in your front yard than stuff that's green and grows, at least here in this part of the country. In East Texas, green and grows, you got no choice on that. You're more worried about elevating your house enough so that it's out of the puddle that comes 3 times a year and occupies the entire county. So in terms of water use per person, we're probably pretty close. Other nations that don't have as much water would be a good guidepost for that if you had a need to estimate the minimal amount. We can't use the absolute minimum that when I was in the Army that we used for planning field hospitals. So field hospital was 25 gallons a day per patient, which is not a lot of water. And when we were playing infantrymen, I think we would plan for, it was either 4 gallons a day per soldier or 3. It wasn't much. And we never got that much to them, but yeah. So in very austere conditions, human beings don't need much water to function, but you start to smell bad pretty quickly. And you itch, and you get big old chunks of skin coming off as you itch. I imagine that was your experience too. And you were in a different part of the world when you were playing soldier. So that gives you some guideposts, but for practical civilization, 100 to 200 gallons per day per person is a reasonable guess of the best you can do. So now we have to figure out how many people there are. Well, there is a technique called population forecasting. Normally, civil engineers don't do this, but we need to be knowledgeable enough to be able to use the results of the geniuses that do it. There are 3 distinct growth phases that can be identified for a collection of people. The geometric growth phase, so that occurs roughly just after the bars close. Arithmetic growth is as the hangover setting in, and then declining growth is after you've gotten over the hangover and it's, oh my God, what have I done? And I apologize if that offended anybody. That was supposed to be funny. So geometric growth is when a population is growing exponentially. Maybe we'll switch from humans to yeast cells. That seems just a little nicer. So you take some yeast cells, you know, the yeast that you get in store to make bread. Well, if you buy bread, somebody got a little package of yeast and put it in the water. And then if you give yeast sugar, which is the alcohol for yeasts, sugar's like letting yeast go to a bar where somebody else is paying the bill. They'll just get everything. And they make a whole lot more yeast cells than that. The doubling time is usually in the hours range, an hour or 2, and the population of cells doubles. And it'll do that for about a day. Then when they've drank the bar dry, they burp and die. That's the geometric growth phase. The arithmetic growth is roughly when the change in population with time is close to some constant. There it's showing it is proportional to 1. It's roughly just some constant. The geometric growth is the change in population with time is proportional to the population. And then the declining rate of growth is we're reaching some saturation value. And so the growth rate, change in population with time is proportional to whatever this limiting value is minus the current population. So it's measuring how close it's getting up to that saturation population line. Globally, as human beings, the planetary population right now is somewhere between 8 and 10 billion. Yeah, with a B. That's a lot of people. As far as the Earth's capacity to support people, that 10 billion is probably a practical limit in terms of water supply, and 11 or 12 billion is in terms of incoming energy. So if we burned all the oil on the planet, it's all gone, done. We burnt down all the trees. The incoming solar energy, if there's something that's can be completely converted to keeping us alive, we can support about 12 billion people. So as a planet, we're probably pretty close to our saturation value. And there's nothing to be ashamed of or sad about. That's just biology. But in individual communities, you know, Lubbock is probably somewhere around B right now. I don't think we're exponentially growing, but we're certainly not declining, at least based on the house prices that I was left campus yesterday, went look at a house, and then I left that meeting and said, I think I just bought a house. Based on the prices, we're somewhere in here right now. So those are the different growth phase. And since we're all civil engineers, don't show me pictures because I barely understand how to operate them. Show me letters of the alphabet and ranging equations because I certainly can't operate them, but nobody else can either, so we're cool. So the exponential growth phase, if that happens to be the phase that we're in, all that says is the population at time 2 is equal to what it is at time 1 times e raised to some exponential growth constant times the change in time. So you had that in calculus class. They probably use different letters of the alphabet because that's how the math building is. They also do all the stuff in chalk. It's disgusting. I teach a class over there, actually this afternoon, and we will all go in there and get gassed by the chalk. Every time we go to that classroom, we all leave. There's 40 of us leave that classroom coughing. It's like, I don't know if it's the chalk or that corona's acting up again. So it's funny at the time, but it's horrible. I used to think the whiteboards were horrible, but I would much rather get gassed by the volatile organic compounds because at least you get some euphoria out of that. Chalk doesn't make you high at all. It just makes it hard to breathe. Our next phase, the arithmetic phase, that's the straight line portion of that curve. Population at time 2 is equal to what it is at time 1, plus whatever the slope of the growth curve is, k sub a, times the time difference, times delta t. And then declining growth, which is the coolest one in the sense that most communities don't acknowledge it, but I know an example of declining growth at the state level. There's a state out there west of here, begins with the letter C, second letter is a vowel, the one that you want to get for this class in a grade sheet. California, it is experiencing declining growth. And in order to use up the remaining U-Haul trailers in the United States, they're about to double their taxes. And that's self-imposed victimhood. So in their case, in California, the case is that the population in 2023 is going to be equal to the population in 2022, which is right now, plus the saturation population minus the population in 2022 times 1 minus e to the minus kd tend to change in time. So that's just the arithmetic of the three things. So if you're planning for the future doing a water design, you would have some need to know what your community's growth phase is in, and you need to ask your sociologists and people that study this. You don't want to ask your chambers of commerce, because to a chamber of commerce, we're always there. And that's their business goal. So you want to grow the community because more people means more tax dollars. Tax revenue for governments and elected officials and college professors is like heroin. Once you get it, you can't get off it. I've never had heroin, so I don't actually know that, but it's funny when you say it. For longer term forecasting, we have to appeal to some different methods. None of the constants are conveniently tabulated. Historical census data are usually used for both short-term forecasts and to some extent long-term forecasts. You all know what a census is because you had that in high school. We just went through one a few years ago. Some of you may have been part-time census workers, where you would go knock on doors in scary parts of town and try to get the number of people that are in there in the house. If the region's been around a while in terms of population sense, then that actual plot that we just did, that might actually be something straightforward to construct. And then you can just extrapolate straight line on the most recent slope, your best guess of exponential growth, and best guess of declining growth, and use that to help guide your design. There's another technique called comparison forecasting, where you take geographically similar areas and you make projections in your design area based on somewhere else. There's a fair amount of uncertainty in these, but that seems to be as defendable a methodology as any other. I think intellectually this seems pretty cool to me. So you have, let's suppose that we are designing something for city A. And we have city B, C, and of course, city D, which would be okay, except that's failing in the College of Engineering. So we care more about B and C. And we know that at some point in the past, city C had a population of 60,000, as did city C, as did city B. And we know our current city A is at about 60,000. So we want to project how A is going to grow. So we simply move the stuff above 60,000 from these three over to this location, O prime. And we say, well, if city A grows like city C by the year 2000, which hasn't happened, which happened 22 years ago, we expect it to be at that population. If it grows like A, if it grows like B, that population. If it grows like D, that population. And you would probably use an average of the three, because when in doubt, guess. And we would postulate that A is going to be somewhere at this point in the year 2000. Then you can use that piece of information. You now have an estimate of population 20 years out, at least according to this chart. And you can use that to estimate your demand for the entire area, for the new region. And finally, ultimately, you can figure out whether to put an 8-inch pipe or a 6-inch pipe in a community. And that's where this is all ending at. There's another technique called our ratio of correlation, which I think is the area equivalent of what was just done up there in those graphs. You look at the observed populations of two study areas, and you make your projection based on the amount in your current population compared to your comparative area. You can also do correlation. And I know that Abby knows how to do correlation. And essentially you're formulating a prediction model of the future based on current conditions. In this case, slope plus some intercept. So there's a lot of different formal tools to help you guess what the population will be in 20 or 50 years. And then if none of that works and you can really convince your client to open their checkbook, you could go to formal population modeling, where you consider birth rates, death rates, net migration rates. The forecasting model simplified looks something like that. It's non-trivial. So getting the values for Cat B, Cat D, and the migration as a function of time is tricky. If you get interested in that, I would recommend finding this book or a copy of it and reading it to get an idea of what population modeling involves. Now, that book is from the 1980s, and I actually worked for that guy when I was a college student. So I feel some attachment to the book because there's a few bits in it that were my work. He was telling me what to do. All I was fingers. There was no brains on my part involved whatsoever. But that's where I learned about population projection, and basically it's throwing dice. So how far should you project to the future? That is a legitimate question. Anybody have any ideas? Good. Why'd you come up with that? It just well, that was a damn good guess. Yeah, 50 years would be your normal projection period, because that is the design and service life of most stuff that we engineer. In the case of Texas, in the Texas Administrative Code, you're explicitly told design, you have to report the flow rate that you're going to use when the facility becomes available, and 50 years in the future. They even tell you that. They don't tell you that explicitly, because that buried in some other pieces. So 50 years, for lack of any other information, a 50-year projection period is probably what you want to use. So now we know how many people we're going to feed. We next need to figure out the per person use and a few of the other components of use. And it boils down to average daily demand, hourly variation if you can get the information, and then fire demand, how many times we're going to set our place on fire. So for per capita water usage, here's some thoughts. The design life varies by component. Maintenance and replacement needs need to be planned for. And sadly, we acknowledge that we need to do maintenance and repair, but we never figure out how to pay for it. So most of our civil engineering stuff gets built and then it breaks and you get built again. Again, job security for everybody in this room, but not the most efficient way to build complicated systems. So here's a picture of two different systems identifying some major components. So if we look on the right side, so we'll look at these pictures from right to left. On the right side, on the upper one, you have a distribution system and a service reservoir. Just think of that as an elevated storage tank, for lack of a better thing to think of. And then we move further upstream into the system, and there's a treatment plant, and then finally, feeding into this treatment plant is a mixed supply. So they're taking one portion from a river in the picture, another portion comes from a well field. So that is a perfectly adequate water distribution system if that's the situation. If we look at the one below, the green shaded areas, those are the same in the two. I mean, both of those situations have those components, but in the below one, we're now taking water from a reservoir. It's 9:15 for anybody that wants to know. Taking water from that reservoir and bringing it into the system. So from a maintenance and operation standpoint, everything in green should have the same maintenance and operation requirements. And the only difference between these two is for the water sources. River and well versus Lake Allen Henry and a conveyance conduit. We do have to consider how long pieces last. So the supply source, a river is considered indefinite. Our well field, 10 to 25 years. I don't think that's until you completely draw down the well, though in West Texas, that's certainly the case. But that's before stuff breaks so much that you have to completely rebuild it. Reservoir, they're showing 25 to 50 years of service life. The conveyance, 25 to 50 years. The pumps, these guys are getting really good pumps because they last 10 years before failure. Treatment plant, 15 years to failure. The reservoir itself, the service reservoir, 25 years to failure. The distribution supply pipe, 50 years to failure. And then distribution grids, they actually don't have an answer, but so all these things are going to potentially fail in slightly less than your design service life. So that needs to be considered. And so keep that in mind when you do a design. And now we want to get to our average daily usage. So our three main categories in an urban area are residential, commercial, and industrial. So the residential is drinking water, landscapes, swimming, fires, street cleaning, and so forth. There's usually two demand peaks per day, the morning and the evening. We talked about that last time. Commercial, hotel, motel, Holiday Inn, offices, shopping centers. There's usually less peak demand and less varied than residential. Commercial is pretty well understood, actually. And finally, industrial. The water use depends on the industry, and industrial uses usually supply their own water. We'll get to that in a second. Now, sometimes your residents have some different configurations. So this is, I think, the coolest apartment I've ever been in. If you live on the upper floors, you go all the way to the roof and you put on your swimsuit and you can go into the dragon's mouth and you run this water slide all the way to the bottom, come out, you change at the bottom and you go to work. That'd be a cool way to go to work. It's like the Batman of apartments. It's not in the United States. So to estimate average daily uses, there are a few tools that are available. In 1995, the United States Geological Survey published Circular 1200. And in that are tables and tables of numbers. They're organized by state. So if you're having to find a number, you probably want to do it to the state that you're working in. And at some point, it comes down to the water use per person per day, depending on the category. It's not the easiest book in the world to use. But if you want to get any number you want, that's definitely the book, because it's got every number in the alphabet in it. Another approach would be to look at our land development handbook and use a tabulation that has average use, gallons per capita per day by different categories. Or you could do how a plumber would handle it, which would probably be what I do, because that uses a lot more numbers and probably helps you size things better. So if you were in the plumbing business, you would have different types of copper pipe, because if you're going to sell your client plumbing, you want to sell them copper and not PVC. Copper is more profitable. And there's flow rates by different sizes. You can use the diameter to figure out what the flow rate is. Most meter to house connections are 2-inch. They may not be copper, but they're 2-inch pipes. So pretty much the most you can get into a single house is 80 gallons a minute. So think of what 80 gallons a minute is. That's all the showers turned on. Shower can produce 5 to 7 gallons a minute. That's your dishwasher running with a broken valve on the discharge side. That can do about 2 gallons a minute. Flushing toilet after toilet after toilet, you get about 5 or 6 gallons a minute. It's hard to use 80 gallons a minute in a house. It can be done. All you need is a nephew and his fiance living with you, and they can use incredible amounts of water. My water bill halved when they moved out. I do miss having the young people lift heavy objects. You could go by the individual fixtures in the home, or you can use a table for rural estimates. My point here, as you're all packing up, as you correctly should do, because I'm babbling endlessly, is there's a lot of ways to estimate potential water use. RG 195 has this table here for water use per person per day based on the type of establishment. So schools where you're not allowed to bathe use 18 gallons per person. Schools where you can bathe use 30. So they're giving you 12 gallons to bathe. And then lastly, the daily variation is the important one. This is taken from the Land Development Design Handbook. It shows the morning peak at roughly 8 in the morning, the evening peak at 7 in the evening, and it cycles back day in and day out and looks like a cat. There's also, in the absence of any way to do daily variation, this formula, which is in Gupta. And we'll pick this up next time because you all got to go. Thank you for your patience and attention. That exercise is due at 11:59 tonight. That's when the server will continue to accept it. So try to get it done and get something loaded up there. She's available at $2 per image. $2 per image to remove the background and do the overlay.
About the next assignment, this stuff being over to the next week, I was wondering, is this due next week?
The next assignment is, I'll have to take a look on that.
All right.
So for the time being, assume it is, but it'll be midnight on Tuesday, so we have time to change.
Thank you. I realize